To the Aspen Plus Physical Properties course, in which we cover mostly physical, thermodynamical, and transport properties of either pure substances, a mixture of 2, 3, or even more components. So this is the index. I just wanted to show you how it's structured. We're going to be talking about each section individually. So first things we're going to cover after finishing with the introduction is the component specification. As the name implies, we need to state the components that we will be using in the simulation or the physical property specification. We're going to cover the component types, that is the conventional one, that those are the easiest to select, those have already pre-existing data on the database and so on. Some solids, non-conventional, Henry components, and all other components which we can select. Then we go to the component groups, how to state component groups, why is it convenient to state component groups, and we're going to be talking about the databases or databanks. Stated before, when we select conventional components, we will be talking about the binary and pure specifications, parameters, etc. Those can be found in plenty of databases which are already in Aspen Plus. Then we go and select the property method, which is one of the most important parts of the simulation, because this is how all the interactions between pure and binary, ternary, and even more components mixtures will be treated. We're going to explain a little bit on theory. I'm pretty sure this is the most exhaustive, let's say, theoretical concepts right here, but it's very important to understand why and how to use it. So we're going to understand what's property method, what's the difference between model and method, how are we going to model ideal, activity-based equation states, and special models. As you can imply, the ideal method uses ideal gas and ideal solution. Activity is mostly based on real solution. Equation of state is really based on real gases, and so on. We're going to use some selection guides, some rule of thumbs in order to choose the best property methods, or even using the method assistant, which is included in Aspen Plus. Then we're going to talk about what's a parameter, why is it important, which type of parameters we can find in pure and binary interactions. Then we go and check out what's a model calculation, what are the different models, and the routes, which is nothing more than the way how we're going to be calculating models. Then we go to property sets. This is a very simple section. It is mostly about on how to select relevant properties that we want to get calculated and reported. This is especially used, for instance, let's say for if you're interested on thermodynamics or more on thermal modeling, maybe you're using heat exchanger or so, you will of course want to know the conductivity, convection, maybe if you are calculating viscosity, all the relevant properties can be calculated here. Or if you are using plenty of study on vapor-liquid equilibrium, you will want to get maybe, the fugacity coefficient, the temperature, pressures, etc. Then we go to one of the most interesting parts of the course, which is the analysis tools. Are here presented. They are the pure properties, binary, mixture, PT envelope, which is very useful for dew and bubble points calculations, for ternary diagrams, and residual curves. Essentially, I like to separate this as either pure, binary system, or ternary system, or plus systems. Depends on the number of substances you use, you will be habilitating these little buttons right here. So if you use only one substance, you will be able to use pure and PT envelope for that substance. You have binary, well, you can use, of course, the pure substance of each component, the binary interaction of those, the mixture, and PT envelope. If you have three substances, you will be able to use all of them because you can interact between them separately via binary. You can use mixtures, and you can use, I will say the most important part will be the ternary diagram. So this is our tools. They are accompanied with some workshops, so don't worry, this is not just theory. We're going to be working on hands-on projects. Then we get to know how can we input data into Aspen Plus. For instance, if you have some, let's say, raw data on vapor-liquid equilibrium and you want to model it by yourself, you can input it here. Or we're going to see some databases which are present already. The NIST database, or the DKIMA database, in which we can get relevant data, actual experimental data on the two models. Let's say that Aspen Plus does not have sufficient information, then we can use this database to get data from. And the most important part of this is not only be able to manipulate the data, but eventually we want to make sure that we can use those data. We can do regression, see how it models each of the different property methods, and eventually reject or accept the data. Then we get to property estimation. As the name implies, we're going to be estimating properties which are not present on Aspen Plus. So this is mostly convenient for non-conventional substances, or substances which are not present in Aspen databases. We can use either the molecule editor, we can use it via property estimation of Aspen, Unifac mostly, or we can state plenty of methods that Aspen has already, let's say, for modeling inexistent materials. Then the most important part of all is, of course, the applications. So more on how do we use the previous tools, the previous theory, in order to get some of study of interest. Let's check out here thermodynamic applications. We're going to be testing models. Let's say equation of states will be maybe, I don't know, Penn-Robinson versus Ralick, Kwong, Suave. Sorry, Kwong, Suave equation. Maybe you want to model, I don't know, your activity. You want to verify the NRTL, which is exactly non-random two liquid models, versus maybe Unifac or Uniquac, or maybe even a Wilson model. Or if you want to get much more basic, into Van Laar model. We're going to compare both of them, when to use each of them. Let's say you have a water ethanol mixture, well, that will be much more relevant to use activity versus activity. If you have a, let's say, butane and pentane mixture, you will most likely use an equation of state, because you're going to have a gaseous state much more relevant than the liquid phases. Then we're going to study on vapor-liquid equilibrium, liquid-liquid equilibrium, and vapor-liquid-liquid equilibrium. This is the typical example where we water, octanol, and hexane. And then we do more on analysis, estimation, regression, and we study, of course, we review pure substances, we review binary system, which I would say is the most important part, and then we check out plenty of ternary systems. Eventually, we go and apply these to real-life scenarios. I call these case studies. I really think it's very important to understand why we need this course, especially in real-life applications. So this is very useful for flash separations, maybe liquid-liquid extraction as well, and distillation units, to understand why we cannot separate some substances via distillation or simple distillation. Eventually, we finished with a course wrap-up, a conclusion, and I will inform you on how can you continue your training. And there is a little bonus section right there. You want to check it out, you are more than welcome.